and thanks everyone from all around the world for joining today. So before my talk, I would like to acknowledge my co-authors and particularly my PhD supervisor, Professor Tatsuki Tsujimori and Daniel Pastagalen. And as I already mentioned in my bio, my PhD research was focused on different orogenic belts, including Central African Shield and Central Asian orogenic belt. In today's talk, I will concentrate on Paleoproterozoic Ubendian Belt of southwestern Tanzania. So my talk will consist of introduction, an overview of my published research, and some results of my ongoing study, which I'm preparing for publication. So our petrotectonic research group, led by Professor Tsujimori, have been working in Tanzania since 2013, and we have published in several papers, which are listed down there. And surprisingly, my paper was the second most downloaded paper from Gondwana research in May to July this year. So as an introduction, our planet is unique by the presence of continental crust. We declare them because the granitic continental crust have long-term record of Earth history. Through the mineral it contains, we can study their history back. So this diagram shows the global detrital zircon database. As most of us know, the global record magmatic age and detrital zircon spectra is likely dominated by accretion of supercontinents, and the available data show at least 5 major magmatic events at 250 million years, 600, and 1 billion years, and 1.8 billion years, and probably at 2.6 billion years. But are these peaks or crustal formation peak or preservation bias is a matter of debate. The map down there shows the distribution of ages of continental crusts. And the Paleoproterozoic era, especially the Archean period, was one of the critical time in Earth history, including accretion of many orogenies than other time, assembly of the supercontinent Columbia, and also the Paleoproterozoic was a period of emplacement from major continental crusts in different parts of the world. One of those venues of Paleoproterozoic crustal formation is the African continent. It consists of Archean cratons, West Africa, Central Africa, and South African Kalahari. Among them, Central African Shield or Composite Congo Craton is built up from several craton or Metacraton, namely Tanzania, Kasai, Angola, Gabon, and Mbomo. Together with San Francisco Craton of Southern America, it's stabilized by the collisions or metacratonization and remained together during the several supercontinental cycles until the Mesozoic with the opening of Atlantic Ocean. The problem of the Central African Shield is the limitation of its exposure and being extensively covered by a Phanerozoic sedimentary basin, plus due to the lack of the study, the actual extent of cratonic fragment and its internal evolution history before the Neoproterozoic consolidation largely remained unclear. And one of the main debate is that the Central African Shield is assembled cratonic fragments, or it's just Metacraton. And this figure shows one of the example of Metacraton hypothesis of Central African Shield constituent, Bangweulu Block. And defining this true shape of the cratonic block have an implication for supercontinent reconstruction and to account the size and extent of the various continental blocks. So let's look in detail. What is Metacraton and what's the difference between them? And here is the initial description of the craton by Bates and Jackson. They defined the craton is a part of the crust which has attained its stability and which has not been deformed for a long time. And this kind of stability is because of the presence of a thick lithospheric mantle and making the craton rigid. And however, those cratons can be involved in continental collisions and be reactivated to generate continental tracts that are no longer craton, but also not a typical orogenic belts. Those resulting lithospheric tracts are Metacraton or a ghost craton. So the definition of Metacraton is a hidden craton that has been remobilized during an orogenic event, but it's still recognizable dominantly through its rheological and geochronological and isotopical characteristics. And the Metacraton hypothesis only holds when the surrounding reworked crust was originally part of the larger contiguous cratonic unit, and they are not segment of other or juxtaposed Archean blocks. So the universally acknowledged example is the Saharan Metacraton of the northeastern Africa. So in this research, we aimed to describe the chemical structure of a Paleoproterozoic unit along the western margin of the Tanzania Craton and determine its timing and the magmatism to reconstruct the tectonic setting, and to identify its isotopic composition and check its internal crustal architecture. So now let's look at the geological framework of the Tanzania Craton and its surrounding belts. The Tanzania Craton is almost entirely built up from the granitoids and greenstone belt. It's surrounded by Paleoproterozoic mobile belts, Usagaran and Ubendian, which shown by yellow here. And the Ubendian belt consists mainly granitoids and gneisses and with magmatite, mafic granulite, and metapelite. On its northern and southern end, the belt is overlain by Mesoproterozoic metasedimentary rocks. And the Ubendian belt borders with the Paleoproterozoic Bangweulu blocks, which believed as a cratonic block. And the Bangweulu block consists of crystalline gneiss, unfoliated granitoids, and felsic to intermediate volcanics. And it is overlaid by thick Paleoproterozoic sediments. And this internal structure of Archean cratons surrounded by internal Paleoproterozoic and outer Mesoproterozoic belt is lead authors to refer Tanzania as a Metacraton. So to zoom in the studied area is a large volume of granitoids and alternizes with both of high pressure and low temperature and low pressure, high temperature metamorphic mineral assemblage have widely spread in Ubendian belt with possible ages between 1.9 to 1.8. It has 7 terrains with distinct geological features, and however, the absolute age for granitoids in westernmost Ubendian belt along the boundary of the Bangweulu Block are scarce. Thus, the tectonic evolution of the metagranitoids in the western margin of Ubendian belt is underexplored. So we sampled metagranitoids, granitoids, and graniporphyries along the two traverses of northeastern portion of the Bangweulu Block and the western margin of the Ubendian belt. And importantly, what makes the Ubendian belt very special is it contains Paleoproterozoic and Neoproterozoic eclogites. Paleoproterozoic eclogites are white stars here, and Neoproterozoic are black stars here. So here are the example of hand sample and thin section photography of Paleoproterozoic eclogites. They are well defined by Professor Boniface 2012 work, and those eclogites have mid-ocean ridge basalt type geochemistry and experienced subduction-related metamorphism between 1.89 to 1.87 billion years. And besides the subduction-related metamorphism, another cryptic metamorphism event was recorded in Mylonitic metapelite that have occurred between 1.86 to 1.82 billion years. And they interpreted that this event is related to an accretion of or a crustal thickening metamorphism that followed after the subduction of an oceanic lithosphere. So as for Neoproterozoic eclogites, they're evidencing Neoproterozoic collision, and it has bimineralic eclogite and the granulated eclogite. Recent study by Isamu Morita, who was the master student here, determined 588 for bimineralic eclogite and 562 million years for granulated kinetic eclogite. And he estimated and modeled that the interval of transition from eclogite to granulated facies was 26 million years. Our studied samples crops out as large granitic battleids, and many samples show foliation, but as they preserved its granitic assemblage, we call them metagranitoid. And their composition varies from metagranite and metagranodiorite. In some samples, occurred metamorphic minerals such as kyanite, garnet, and epidote. So we analyzed 9 samples in total. This figure shows examples of cathodoluminescence image of the representative zircons. So most of zircons have oscillatory zoning. We didn't find any inherited cores. So this right-hand side plots are thorium versus uranium and ratio of these elements versus age. As we can see here, most of the samples, the zircons had an igneous origin as it has more than 1.0, and few zircons had thorium over uranium ratio less than 0.1, implying its metamorphic overgrowth. So here are some concordate diagrams of data samples. So several zircons of 2 samples show lower intercept age of 570 to 565 million years, and which is within the range of that Neoproterozoic eclogite. And the rest of the samples show age from 1.89 to 1.85 billion years. And we also analyzed the whole rock geochemistry. By trace element geochemistry, our samples show geochemical feature of the slab melting in high pressure environment. So these are some of the diagrams recently developed by Wallen and Hildebrand to distinguish high pressure slab melting and arc. So main features to distinguish them are high strontium over yttrium and gadolinium over terbium ratio, suggesting the presence of garnet without plagioclase in residue. And high niobium over yttrium and tantalum over terbium ratios are suggesting the residual garnet and absence of titanium-rich phase such as titanate. So in brief, these features reflect that the melting occurred in a high pressure or in a greater depth. So if trace element features show that the magmatism formed in a greater depth, we suggested the slab break-off scenario. So why we need to break them? And as we have collision event followed by subduction, due to the buoyancy contrast between the oceanic and continental lithosphere, every collision that marks the closure of the oceanic basin must involve the break-off of the subducting slab. It occurs typically near the continental and oceanic join. By pressure release, melting of the garnet-bearing rocks will rise to the continental margin and resulting voluminous granitic battleids. So more evidence comes from sedimentary record. The Bangweulu Block overlaid by Paleoproterozoic thick sedimentary formation with 2 different sequences. And the previous study interpreted that the lower sequence formed by uplift and the upper sequence formed by inundation, and they originated through the collapse of the crust. And the Ubendian Belt and the Bangweulu Block of them within the amalgamation of the Central African Shield participated as a separated unit during the 1.9 to 1.8 billion years. And this figure shows global distribution of the slab-failure magmatism. Another Paleoproterozoic examples are reported in the Vathaman and Kimberley battleids in Canada. And early to mid-Paleozoic cases are in Newfoundland and Grampian, orogeny, and the Mesozoic examples are in Sierra Nevada and peninsular and coastal batholiths of America. And the youngest examples are in Tibet. And the ages of those slab-failure magmatisms are also overlaps with the peaks of the global detrital zircons. And Wallen and Hildebrand suggested that the slab-failure magmatism can provide another interpretation for those crustal growth peaks, which were previously interpreted to represent the preservation bias. As I introduced it in my beginning of my talk, those peaks are overlaps with the periods of supercontinental assembly, and they might reflect the periods of increased collision and hence the increased slab-failure magmatism. So we added the Paleoproterozoic case from East Africa. So as most of you know, but before to move on the next part, I would like to briefly remind what can tell us the zircon hafnium isotope and how it works. So this diagram is the epsilon hafnium plot versus age diagram, and you can see this in every paper used hafnium. And the epsilon notation is notation obtained from ratio of the measured zircon 176 hafnium over 177 hafnium, divided by those ratios of chondritic uniform reservoir. So if you look at this diagram, and once crust is separated from the source, normally it will evolve along the hypothetic lutetium over hafnium ratio, which shown here is a negative slope. And the positive value means zircon being magma is recently extracted from the mantle source, and the negative value indicates the reworking with the pre-existing crust. So as we can measure the hafnium ratio, then we can just calculate how those zircon would have evolved back through the time. And the time when it hit the depleted mantle evolution line, name is a modelage, that is a mantle extraction age or crustal emplacement age. So I focused on hafnium in zircon isotope, trying to understand crustal evolution and spatial distribution by isoscape. Our new compiled data aim to contribute to the understanding of the crustal architecture of the Tanzania Craton. So these are the histograms and probability density plots of igneous zircon with hafnium values of Tanzania Craton. So I separated them by different blocks and avoiding to use too many local names. I named here a geographical location name, but if you're familiar with the Tanzanian geology, here is the block names. So the histograms show that the oldest magmatism in Tanzania Craton took place in southern area at about 3,000 million years, and then later in the central part and in the Ubendian Belt at 2.85 GA. And at above 2.65 GA, crust in place in the eastern and northern part. So how about the hafnium isotope? So the oldest crust, which shown by orange circle here, has a chondritic value, and 2.8 zircons of the Ubendian belt has suprachondritic value, showing the initial maybe suggesting the initial extraction of cratonic crust, and the 2.65 zircons of southern part having the most negative values or reworked hafnium values and clustered around -1 to -3. And the zircons from the central part has a closer value, and the zircons from northern part, which is a gray square here, shows mostly suprachondritic value. To check its spatial distribution and crustal architecture, we did hafnium isoscape or hafnium isotope mapping. This isoscape is drawn by interpolation method in QGIS. This approach to reveal the crustal architecture is developed by David Moll and very successfully used in Ilgan Craton of Western Australia to seek the isotopically juvenile domain, and he linked that with mineralization. So my initial goal was to use this approach to all cratonic fragments of Central African Shield, but unfortunately, I used enough data only for Tanzania Craton. So here is the epsilon half-name distribution of the Tanzania Craton, and each point here represents the median value of epsilon half-name of each sample or the closer sample. The red dots here are uranium lead age, and as older the rockets, it becomes more red. We can see here that regardless its uranium lead age, the domain with the most negative half-name value is formed in the southern and eastern part of the Tanzania Craton, and the more radiogenically juvenile or radiogenic crustal addition in places at the northern and central part and Ubendian Belt. So in case of Paleoproterozoic, the Bangweulu Block and Ubendian Belt has more radiogenic value than the Eastern Ubendian Belt. And the data for the Bangweulu Block and Western Ubendian Belt comes from our study. And we can see here that they have mostly almost similar zircon peak, and here show the mixing between the radiogenic and non-radiogenic crust here. So here is the spatial distribution. We can see here that the domain with most negative values had in a southern part, and the radiogenic juvenile crustal addition to be placed in the central Ubendian Belt. So this architecture is argued against the Metacraton hypothesis. So during the Paleoproterozoic, that the cratonic margin of the Tanzania Craton is not fully reworked in Paleoproterozoic. In contrast, it experiences the new crustal addition during this time. So in addition to our crustal architecture, and this Ganwana research paper, 2013 Ganwana research paper by Legos, he proposed the criteria for Metacraton and reviewed all suggested Metacraton. And here is the 6 main criteria for Metacraton. So let's look if Tanzania Craton fulfilling those criteria. So first one is the absence of the pre-collisional event. So I already mentioned by magmatism, by slab-failure magmatism and the Paleoproterozoic eclogite, that we have pre-collisional events. And absence of the lithospheric thickening, subduction related metamorphism, we have eclogites, and the preservation of allochthonous pre-collisional terrains. We also show that there is a this criteria is no works, and abundant post-collisional magmatism. The post-collisional magmatism in the Ubendian Belt appears only later than 1.7 billion years. The only criteria which have Ubendian Belt is we have high temperature and low pressure metamorphism, and the last criteria is the intercontinental orogenic belts unrelated to the subduction and oceanic closures. This criteria is also no works. So in addition, the recent study by Saley et al., they showed the three-dimensional representation of cratonic lithosphere in the tomographic model, and they showed that the no cratonic root beneath the Bangweulu Block, and they suggested the probable presence of the cryptic Craton south to the Bangweulu Block, and named them as a Nyasa Craton. So if Bangweulu Block and Tanzania Craton was separated units during the amalgamation of Central African Shield within the frame of Colombia supercontinent. The at least Kasai and Angola Cratons were separated units from the Tanzania Craton. So here are the key points from my study. The chemical structure of Paleoproterozoic continental margin in the southwestern Tanzania is characterized by high pressure slab melting, and the timing of the magmatism varies from 1.89 to 1.85 billion years, and slab-failure magmatism was a component of supercontinental Colombia. And the crustal architecture showed that the Tanzania Craton and Bangweulu Block was a separated unit during the assembly of the Central African Shield. And I would like to end of my talk by the splendid granitic battles of Central Mongolia, where I am from, and which was also my study target, and the sort of fieldwork which I participated in 5 years ago. And that's the end of my talk. I'm happy to have questions and comments.